everyone. Welcome to Gate Pass. In this video I am going to take problems that were related to thermodynamics and which appeared in Gate 2012. Okay, so the first problem which I have selected, it involves throttling of an ideal gas. After throttling, the pressure reduces by 50%. They say that if the ratio of Cp by Cv is denoted as gamma, then you have to find out that the specific volume, it changes by what factor. Okay, so they have given you 4 options and you have to find it out which one is correct. So let's first quickly see what are throttling valves or throttling devices. Okay, so throttling valves are nothing but the flow restriction devices. Okay, so let's say that there is a plug which is kept in between the pipe through which the flow is taking place. Let's say that the inlet pressure is Pi and inlet temperature is Ti, exit pressure is Pe and the exit temperature is Te. Because of this flow restriction, what happens? Your pressure drops, so Pe is less than Pi. This pressure drop, it is not accompanied with any work, unlike turbine. In turbine, what happens when your pressure drops? You extract some work out of it. Okay, in this case the pressure drop, it is accompanied by a change in temperature or a drop in temperature. Okay, so for real gases, if you throttle, your Te is less than Ti in most of the cases. Okay, so I have written my general energy balance equation. Right now let's simplify this for the throttling valve. Since this is a very small device, so we can neglect any heat exchange between this. So this is my control volume. So we can neglect any heat exchange which is taking place. Okay, work done, we have seen that it is equal to 0. Let's assume that there are no elevation changes, so potential energy change is 0. Let's assume that the kinetic energy changes are also 0. If we assume a steady state, then this term is also 0. So what you are left with is basically that delta H is equal to 0. If you have delta H that is equal to 0, that means your inlet enthalpy is equal to your exit enthalpy. So basically your throttling device, it is a isenthalpic device in which your enthalpy remains constant. Okay. Now let's see what happens if you throttle an ideal gas. So for an ideal gas, you know that your internal energy, it is a function of temperature only. Okay. Similarly, enthalpy, that is given by U plus PV, where I can write U is a function of temperature. PV I can write for ideal gas as RT. So your enthalpy is also a function of temperature only. Okay. So if your enthalpy at the entry and the exit, it remains the same, then your inlet and exit temperature also remain the same for throttling an ideal gas. Okay. Now let's use this equation now. So my inlet and exit enthalpy are same. That means I'm just going to expand it. So H is equal to U plus PV. So I'm going to write it like this. That is equal to UE plus PEVE. Okay. Since the temperature is not changing, my internal energies will remain constant. So they will cancel out. What I am left with is PI is equal to PEVE, or I have to find out the ratio of VE by VI. So let's rearrange this equation. That is equal to Pi by PE. But PE is 50% of Pi. That means PE is equal to Pi by 2. Or that means that the factor by which your specific volume changes is 2. Okay. So your option A is correct. So this was very simple and very straightforward. So what we have seen over here is that if you throttle an ideal gas, your temperature does not change. But for real gases, your temperature changes. Okay. So let's quickly see what happens if you throttle a real gas. So for a real gas, let's say that I have fixed my inlet pressure and inlet temperature, and for varying exit pressures, I am plotting my exit temperatures. Okay. In that case, I obtain isenthalpic curves in which take the form something like this. So up to a certain point, you observe that your slope is positive, and after that your slope becomes negative. Okay. So this is known as your inversion point, and the slope of this curve is defined as mu Jt, that is del T by del P at constant enthalpy. Okay, this is your Joule-Thomson coefficient. So when you are in this region before your inversion point is reached, okay, in this case your mu Jt is positive. If your mu Jt is positive, okay, that means for a decrease in your pressure, your temperature also decreases. Okay, so when your mu Jt is greater than 0, then throttling that gas, okay, it will cause a decrease in temperature. But if you are beyond this inversion point, your mu Jt is negative, that means less than 0. In that case, if you decrease the pressure, your temperature will increase. So if any gas, it has a Joule-Thomson coefficient which is greater than which is less than 0, then on throttling its temperature will increase. So most of the gases, usually they show a Joule-Thomson coefficient which is greater than 0 and a decrease in temperature on throttling. Okay, but some of the gases which have an inversion point at a temperature which is below the room temperature, in that case you do see that the temperature increases on throttling. This happens for hydrogen, helium and neon. That's why it is a hazard. If you have a hydrogen cylinder which is leaking, then it can cause explosion, because on throttling the temperature increases. Okay, because its Joule-Thomson coefficient is less than 0. Okay, so this is all about your throttling process. Now let's move on to next problem. So the next problem which I am going to take, it involves parallel flow heat exchanger. So you have a hot fluid which is going in at these conditions. So this is my flow rate of the hot fluid. This is the entropy of the hot fluid which is going in. This is the temperature, and similarly you can see these are for the cold fluid. These are the conditions for the hot and the cold fluid which are going out. Now they have said that which of these statements is true. Okay, so for this problem we are going to use our entropy balance. I have written that for you. Further I have simplified it, that for steady state this term will be 0, any change with time will be 0. Okay, this term, it gives you the entropy change of the surrounding. Since they have asked you to neglect all the heat exchange between the this heat exchanger and the surrounding, so you can also take, because Qi is 0, you can take this term as 0. Okay, so what you are left with is just these two flow terms, and that is equal to your entropy generation term. I am going to just retain the simplified form of your entropy balance on the board. Okay, now let's write these terms in the variables which we have fixed for this parallel flow heat exchanger. Okay, so the entropy which is going out, I am going to write as, okay, so first of all I will write for the hot stream, so that will be equal to m dot h SHO plus m dot c SCO, okay, out, minus in, so minus in will be minus m dot h SHI minus m dot c SCI. Okay, and this thing should be equal to your entropy which is generated. Okay, yeah, SG. So this is equal to your entropy which is generated. Now let's rearrange these terms. Okay, so I will take m dot c common outside, and then I will write SCO minus SCI. Okay, minus let's take out m dot h common outside. Okay, and then write down SHI minus SHO. That is equal to your entropy generation. Okay, I have just rearranged these terms, taken out the mass flow rates, and then rearranged these equations. Now look closely, what is SCO minus SCI? Out minus in. Okay, so this is your entropy which is gained by the cold fluid. So I can write that this is my entropy gained by cold fluid. Okay, minus, what is this? entropy of the stream which is going in minus entropy of the stream which is going out. So this is this minus this is the entropy of the which is lost by the hot stream. Okay, so I can write entropy lost by hot stream. Okay, and that is equal to entropy generation. Now you all know that for this any process, okay, this entropy generation term is always positive because of irreversibilities in this process. Okay, so this is always a positive quantity. That means that entropy gained by cold fluid is greater than your entropy lost by the hot fluid. That's why this is a positive term. So that's why I get that entropy gained by cold fluid is greater than the entropy lost by hot fluid. So your option A, which gives you this statement, is correct. All other are wrong. Okay. So this was very simple problem which was based on entropy balance. So the next question which I am going to take is question number 9. It asks you that for exothermic reversible reaction, which of these statements is correct regarding your equilibrium constant K. Okay, T and P are your temperature and pressure respectively. Fine. So let's see how K is defined. We have seen that K, that is defined as exponent of minus delta G0 by RT. Okay. Now delta G0, which is nothing but your Gibbs energy, standard Gibbs energy change of reaction. So delta G0 is given as summation over all I nu I Gi. Okay, and Gi is your Gibbs energy of pure species in standard state. Gi is independent of pressure. It is just a function of temperature. Okay, so that makes your delta G0 also independent of pressure and it's a function of temperature only. So since K is related to your delta G0, that means that your K is also a function of only temperature. So in these options, wherever it shows a dependency of pressure, then those options are wrong. Okay, so K is independent of T and P? No, K is dependent on temperature. So this option is wrong. K increases with increase in T and P. You can say something about temperature but not about pressure. Okay, so this is also wrong. K increases with T and decreases with P. No, it's not a function of pressure, so this is also wrong. K decreases with an increase in T and is independent of pressure. So of course we know that equilibrium constant, it is independent of pressure by its definition. Okay, and K decreases with an increase in T. We know that for an exothermic process, if you increase the temperature, then your equilibrium constant decreases. Okay, so this option is correct. We will briefly see how you get this result that your K decreases with an increase in T for an exothermic reaction. Okay, so let's see how do we get the relation which tells you the temperature dependency of K. Okay, so to start with, I am going to write one equation which is very general form. So I will write dG by RT, and that is equal to 1 upon RT dG minus G upon RT square dt. Okay, so what I am doing basically over here is keeping T constant, then taking derivative of G, then keeping G constant and taking derivative of T. So this is a very general equation. Now what I am going to do is put the definition of dG and G over here. So I can write, let's take RT common outside. dG is nothing but your VdP minus SDT minus G is H minus Ts. Okay, RT I have taken out common outside, so the remaining is only T, and it's multiplied with dt. Okay, now let's open the bracket. So what you have is VdP minus SDT, okay, minus H by T dt. T will cancel, so I am left with SDT. Okay, now this SDT will cancel, and so now this equation becomes V upon RT dP minus H upon RT square dt. Okay, and this is equal to d of g by RT. Now let's take a partial derivative of this term with respect to t while keeping p constant. What I get is that del g by RT upon del t at constant pressure, that is equal to minus h upon RT square. Okay, so this is a very general relation. Okay, now if I write this equation for Gibbs energy of pure species I in standard state, okay, so I can write this equation for GI0 as well, and then here it will be HI0. So I can write this equation for pure species in its standard state. Okay, now let's say for a reaction I have I species, I can write this equation for all the I species. If I multiply them with their corresponding stoichiometric coefficients and then add these equations, then d of delta G0 by RT, okay, by dt, it is temperature by dt, okay, that is equal to minus delta H0 by RT square. Okay, but we know that minus delta G0 by RT, that is equal to ln of k. Okay, so I can write this now as, I will erase this. So the relation which we get is, what I will do is I will take the negative sign over here, and then I can write this as d of ln k by dt, that is equal to delta H0 by RT square. Okay, now if you have a exothermic reaction, then your delta H0 is negative. Okay, so this is negative, that means d ln k by dt is negative. That means if you increase the temperature, your equilibrium constant will decrease. Okay, similarly if you have your delta H0 which is positive for your endothermic reaction, then in that case if you increase the temperature, your k will increase. Okay, so that's why in that final option which was given for this problem, it said that the k decreases with an increase in T. Yes, it was an exothermic reaction, so if you increase the temperature, your k will decrease. Okay, so this was a brief description. Now let's move on to the last problem. The last question which I am going to take is question number 31 of GATE 2012. In this they say that you have a binary liquid mixture at constant temperature and pressure. Okay, now they have given you the enthalpy change of mixing is given by 5 times x1 x2, where these are the mole fraction of component 1 and 2. Okay, similarly they have given you the entropy change of mixing delta S, it is given by this relation. Now they have asked you to find out what will be the minimum value of Gibbs free energy change of mixing at 300 Kelvin. 4 options have been given and you have to find out which one is correct. Okay, so in this case what you are going to do, you know that your delta G, that will be equal to delta H minus T delta S. Okay, so plug these values, what you get is 5 x1 x2 minus T delta S, so minus R times T x1 ln x1 plus x2 ln plus x2 ln x2. Okay, so this is the relation which you get. Now I can put x2 in terms of x1, so I can write, instead of x2 I can write 1 minus x1, and this also I can write as 1 minus x1. So I have now, okay, this x2 also I can write as 1 minus x1. So now I have written my Gibbs free energy change of mixing as a function of x1 only. Now if I have to find out at what x1 you will have a minimum value of Gibbs free energy change of mixing, what I will do is I will take a differential of this with respect to x1 and then equate it to 0. So that's what I am going to do, and if I do that and solve this equation, I directly get this relation. You can do it for yourself and see whether you reach this. So ln x1 upon 1 minus x1 plus 5 minus 10x1 that is equal to 0. So this is the equation which you get after differentiating this relation and equating it to 0. Now the only step which is left is that you can solve this equation and find out the value of x1. Since the values of probable values of x1 are given, so what I will do is I will plug these values in this equation and see which one of them satisfies this relation. So if you do that, you will see that x1 equal to 0. Right away you can see that this is not satisfied. For x1 equal to 0.5, you will see that this relation is satisfied. You will get RT ln of 0.5 upon 0.5 plus 5 minus 10 times 0.5. Okay, that is equal to 0. Let's see if this term is 0. 0.5 by 0.5 is 1. Ln of 1 is 0. So this term is 0. 10 multiplied with 0.5 is 5, 5 minus 5 is 0, so this term is also 0. So this equation is satisfied when your x1 is equal to 0.5. So this is the right answer. So this was a very simple problem. The only time consuming step was to take a differential of this, equate it to 0, which I have not done. You can do it and check with my answer. You should get this relation. So I hope you like my teaching, and if you like this video, please don't forget to subscribe to my channel, and thanks for watching.